In this video, we will talk about numerical linear algebra. If you have been watching my channel before, I've been specifically talking about LeetCode problems, how to solve those puzzle problems. I've been thinking myself, if we are using algorithms to solve those puzzles, why shouldn't we talk about numerical linear algebra, which I think is more important than, say, LeetCode problems. And also my field of interest is computational photography, and numerical linear algebra is crucial. Like, the techniques coming from the numerical linear algebra is really important. That was my motivation. So let's get started. So motivation is that linear algebra is everywhere. So like finite element method, computational fluid dynamics, that's really on numerical linear algebra. Matrix decomposition, so we have singular value decomposition, which is used in signal processing, also used in Google's PageRank algorithms. And there was this about 10 years ago, we had a Netflix computation where we come up with our own recommendation algorithms, and singular value decomposition is used there too. We also have robotics, circuit design, and circuit simulation. We also have aeronautical engineering, statistical learning theory, so machine learning, computational photography, convex optimization, and so on. So you can see that this is very important field. My goals are that hopefully I will talk a little bit about theoretical part of linear algebra. I want to spend a lot of time on numerical linear algebra. I also want to talk about randomized numerical linear algebra. I also want to talk about some advanced topics, like we can talk more about the properties of special matrix, like Toeplitz matrix and so on. We can also talk about the compressed sensing. So compressed sensing is a huge topic, like 2010 I think. So that will be my goals, and I have to tell you, I don't know if I can accomplish my goals, but anyway, those are my goals, and I plan to talk all about them. I plan to have more coding example like in this upcoming series of lectures, so you will see more of the Python codes or Julia codes, because in my view, if you know how to write a code, in addition to proving why algorithms works or not, that is the best way to truly understand the topics. So instead of talking about all the theoretical parts of linear algebra, I want to talk about, obviously I cannot talk about like all the basic linear algebra because they will take so much time. For this video only, and maybe next video, I will talk about the basic part about the linear algebra, and then I'll just I'll go straight into the numerical linear algebra. And if we haven't seen this like theoretical parts or the results theorem from the linear algebra, then I will mention this as we move along. So I think that will be better. If not, I can improvise, but that's for another topic. Jack Dongara, he's well-known figure in the scientific computing, or supercomputing too. And back in 2000, he listed the top 10 algorithms of the 20th century, and then including 20th century. And among those 10 algorithms, I pulled out the algorithms that were coming from numerical linear algebra. So you can see that we have 6 out of 10. I think the first one was Metropolis algorithm, so that's Monte Carlo stuff. And I think another one was quicksort algorithms, for sorting. And I don't remember on top of my head the other 2. But anyway, so we have 6 here. We have simplex method for linear programming with interior point methods. We have Krylov subspace iteration methods. So we have a conjugate gradient, GMRes, MinRes, something like that. We also have matrix factorization algorithm like LU decomposition, Cholesky QR. The purpose to solve linear system, do linear least squares, etc. We also have a QR algorithms for computing eigenvalues. We have FFT. I think most of us have seen this FFT. We also have fast multiple method. You can see why numerical linear algebra is quite important, right? So we have, if some field has more than half of the top 10 algorithms coming from that field, I think it is worthwhile to study the field. At least that's my view. So I will talk briefly about the matrix multiplication. So I will talk about column space of a matrix, and that will be the end of the video. But we have encountered dot product. So what is a dot product? We are given 2 vectors of size n. So x and y are in our real number of n dimensional. So we have this x transpose dot y that's equal to this guy, and this is the dot product, and this is what's going on. So when we say x is in our a real number of n dimensional, so this is how we write it: x1, x2, all the way to xn, and then we have x transpose. So so this guy is what, n by 1 matrix. When you transpose it, we get 1 by n. So x transpose dot y this is what we get, and we have a number. So this is just a natural number, a real number, right? So it is some number. So dot product, we get some number. And why do we care about the dot product? Sometimes you want to know the length and angles among the vectors, and this is needed. So dot product is needed for that purpose. So this one is about matrix vector multiplication, and like in high school and maybe in the freshman year or sophomore year or college, like when you do when you calculate matrix vector multiplication, like we do this using our hands. When we do that, we had this, right? We had like A11 all the way to AM1. So this is our matrix A. It's just n by n matrix. That will give us what? We take the first row and then we dot product that with x vector. So that's what's going on here. So row 1 of A all the way to row m of A, and then we have x1 all the way to xn. And then this guy is row 1 of A dot x, or dot dot dot, row all the way to row m of A dot x. So you see that this is this works. There's nothing wrong with that. For better understanding, I think the other way is better. Here in this case, we have a linear combination of the column vectors of A. If you notice here, this A11 all the way to AM1, this is our column vectors of A. Here, the first column vector, all the way to the last column vectors of A. So that's A1n all the way to AM, and we still get the same answer. However, this one is a bit unique because it gives us that geometric understanding of what's going on for the matrix vector multiplication. In other words, one example is that later in this series, I will talk about conjugate gradient method, and it is a little bit difficult to understand because, just like many math papers, like you have this algorithm and then they show why this algorithm works, but we never get that intuition, like how did this person come up with this, right? There is this paper on conjugate gradient method by Berkeley professor Shuchuk, and he wrote a phenomenal articles on that, like how he used geometric intuition to understand the conjugate gradient method. And that was the moment I realized, if I can, I will try to use geometric analogy to see what is going on. It doesn't work all the time, obviously, but if I can, then I'll try to use geometric intuition. So we have this one. AX is just a linear combination of the columns of A, column vectors of A. So we have x1 some number with first column vector all the way to xn with the last column vector of A. So that's the first part. That's what this means. Second part is just an example. Say we have a 2 by 3 matrix. My question is, actually you can see that this matrix does not fill the entire. This one should be space because plane is 2-dimensional. So space. So we have 2 by 3 matrix does not fill entire space of our R3. Why is that? Because we have x1 and x2. Even though our column vectors of A are in R3, we need one more independent column vectors, and then we can fill the entire space of R3. In other words, let's look at the example. My question is this vector B 1, 0, 1, is this in our column space of A? That's asking if you can come up with values x1 and x2 in this case, such that B is equal to AF. If you can find the value x1 and x2, then B is in our column space of A. If it is not, then it is impossible. Well, here we only have 2 column vectors of A, so if we have 3 independent vectors, column vectors, then the answer is yes. But since this is not the case, answer is no. Let's see why. B equals AX. This is what we have. You can use the first 2 equations to find the values of x1 and x2, and we get 2 and -1 for x1 and x2 respectively. Now notice that if you plug these values back into our third equation, we don't get 1, we get -1. So we get a contradiction, so that's why this is false and B is not in our column space of A. Another thing that we can find is that whether column vectors are independent from others. In this example, we have 2, 3, 4, that's one column vector, 3, 5, 5, that's second column vector, and 5, 8, 9, that's the last column vector. Notice that you can add column vectors of this first column vector and second column vectors. Then we get 5, 8, 9, which is exactly the last column vector. We have this redundancy going on here, and that means our column vectors are dependent. So our column space A in this example is just 2, 3, 4 and 3, 5, 5. So this is the last slide of this video. So the column space of n by n matrix A is the set of all linear combination of column vectors of A. And in some book they use R of A. R stands for the range of matrix A, but I will use C of A. It's a lot simpler, column space of A. And we say span of A1, A2 all the way to AN. This A1, these are column vectors of matrix A. There are two things that I want to mention before we end this video. First is that column space of A is explicitly defined, meaning that we know exactly how to build a vector that belongs to our column space of A. Another thing is that column space of A spans the real number of m-dimensional space if and only if Ax equal B has a solution for every single vector B in m-dimensional real number space. That's for this video. Hope you guys enjoy your weekend, and I will see you soon.